Welcome to today's Explainer. Today, we're uncovering the hidden infrastructure and, honestly, the massive logistical hurdles required to make sustainable flight a reality. You know, we always hear about those sleek, futuristic aircraft being designed for tomorrow, but today, we're going to look down at the ground. We're going to explore the massive, unseen engine of the green transition that literally has to be built before those planes can ever take to the skies.
It's a question we've probably all asked ourselves at some point, right? I mean, we have electric cars in our driveways, electric buses in our cities, but where are the electric planes? Well, the truth is the aerospace industry is working tirelessly on them. But the bottleneck isn't just getting a heavy battery to fly. The unsung heroes, and quite frankly the real bottlenecks of this whole green transition, are the airports themselves. To support electrified aviation, our airports are going to have to undergo a transformation so radical, it will fundamentally change how they operate and how they consume power.
Okay, let's jump right in. Section 1. Meet the electric fleet. More than just batteries.
So the solution to electrified flight is definitely not a one-size-fits-all situation. When we say electric aircraft, we aren't just talking about a plane with a giant battery stuffed inside. The architecture ranges from fully electric systems to incredibly complex series and parallel hybrids. Some of these use batteries combined with traditional internal combustion engines, while others use sustainable aviation fuels or hydrogen to actually generate electricity while up in the sky. And this incredible variety means an airport can't just install a standard wall plug and call it a day. They have to cater to a really complex mix of energy demands. Now, what's truly fascinating is that some electric planes won't even use batteries at all. Take the turboelectric aircraft. This setup uses an internal combustion engine to drive a generator, which then powers the electric motors for propulsion. And this completely flips how we think about their fuel needs on the ground. A turboelectric plane doesn't need to plug into the local power grid to recharge. It needs a steady supply of liquid fuel. So future airports must be able to simultaneously manage high-voltage electrical charging and the supply of advanced liquid fuels. It's a massive balancing act.
Moving on to Section 2, the Great Charging Challenge, time versus power.
All right, so airports will have to choose between three main charging strategies for the apron: a mobile charging truck, a direct plug-in cable right at the gate, or physical battery swapping. And let me tell you, each of these carries a massive logistical footprint. A mobile truck? Well, it allows an aircraft to park literally anywhere, but that truck itself is basically a rolling multi-ton battery that needs constant recharging. Plug-in cables are kind of what we use for cars, but for planes, these cables are massive, they're super heavy, and they require immense power. And battery swapping? Well, that requires a completely new, incredibly complex ecosystem out there on the tarmac. Comparing the plug-in method versus battery swapping reveals a really difficult trade-off between stressing the local electric grid and demanding massive physical storage space. Plug-in charging is a pretty mature technology. It's cheaper to install initially, but it draws a tremendous, wildly fluctuating amount of power from the grid all at once. Battery swapping, on the other hand, is incredibly fast. You just pull the depleted battery out, slide a fully charged one in, and boom, the plane is ready to go in minutes. It also allows the airport to charge those spare batteries slowly and steadily over time, which, trust me, the local power grid absolutely loves. But the catch? You need vast physical storage space to house all those extra batteries, plus you need absolute standardization across all airline manufacturers. And getting everyone to agree on one battery size, that is a massive hurdle. To really understand the sheer grid stress caused by plug-in charging, just consider this number: 3.75 megawatts. That is the capacity of the upcoming megawatt charging system standard. For a little context, a standard fast charger for your electric car back home might draw, say, 150 to 350 kilowatts. We are talking about an absolutely astronomical spike in power demand for just one single aircraft. Now imagine 5, 10, or maybe 20 of these aircraft plugging in at the exact same time at a busy hub. The local power grid would simply collapse without some major upgrades. Now you might be asking yourself, why do they need to charge so fast? Why do we need to draw 3.75 megawatts? Well, because these massive power spikes are entirely necessary. You see, airlines operate on razor-thin margins and strictly scheduled commercial turnaround times of just 30 to 35 minutes. They simply cannot afford to extend their standard gate turnarounds just to sit around and wait for slow-charging batteries. If an aircraft is sitting on the ground, it is literally losing money. It has to be charged in the exact same amount of time it currently takes to pump in regular jet fuel.
Let's look at how we fixed this in Section 3, redesigning the modern airport, airside versus landside.
To actually integrate all these solar arrays, hydrogen facilities, and huge battery storage systems, the very geography of the airport has to change. Think about it. Airports are strictly divided into the land side, where we park our cars and check our bags, and the air side, the highly secure zone with the runways and gates. The integration of all this new technology has to happen across both of these zones, but the airside is where the absolute most complex engineering is going to take place.
The airside alone is going to require some incredibly complex new additions. Aside from those specialized megawatt plug-in cables at the gate, we're going to need external battery temperature regulation systems. Because, think about it, when you push megawatts of power into a battery, it generates intense heat. Aircraft batteries will likely need to be hooked up to massive external liquid cooling systems right out there on the tarmac just to prevent them from overheating and degrading during a fast charge. Plus, because battery power is just so precious for flight range, planes aren't going to want to waste that energy just taxiing to the runway. This means a whole new fleet of heavy-duty electric tugs will be required to physically tow the aircraft all the way to the runway threshold.
All right, Section 4, Fueling with Alternative Energy, Going the Distance. When we try to solve the massive weight issue of batteries for those long-haul flights, two main contenders emerge: liquid hydrogen and sustainable aviation fuel, usually just called SAF. But both of these bring their own incredible logistical nightmares right to the airport's doorstep. SAF is honestly a dream for infrastructure because it can just be stored in standard existing aviation fuel tanks. Easy, right? But hydrogen? Oh boy. Hydrogen requires cryogenic tanks chilled to -253 degrees Celsius. And actually, producing that liquid hydrogen right at the airport, that would require immense, mind-boggling amounts of electricity for the electrolysis and liquefaction processes.
So, you might think, okay, let's just make SAF everywhere. But the feedstock limitations are actually really severe. To put this into perspective, converting all flights in a country like Sweden to biojet fuel would consume up to 15% of their total national biomass. 15%! That puts aviation in direct, head-to-head competition with things like road transport and district heating for those same biological resources. Because of this, producing SAF directly at the airport just isn't realistic. It has to be produced at massive, centralized national facilities and then piped in.
This brings us to Section 5, Generating and Storing Power, the airport as a power plant.
Because of these immense energy needs, airports are exploring absolutely everything to generate their own power on site. We're seeing proposals for geothermal energy and even biomass combustion. Wind turbines are also technically an option, though wind power is heavily restricted in these spaces. I mean, you can't exactly plop giant spinning wind turbines right next to an active runway, right? The tower height is an obvious crash hazard, and those massive spinning blades cause severe radar interference. Because of all this, solar power has really become the undisputed favorite for airport electrification.
And solar power actually offers some incredible synergy in certain regions. There's a fascinating case study in India that demonstrated this perfectly. They found that the peak generation of their solar power perfectly matches the peak electricity demand required to cool down their massive terminal buildings during the absolute hottest parts of the day. It is just a brilliant alignment of supply and demand. But of course, like literally everything else in aviation, integrating solar panels is highly complex.
Because let's be real, you can't just throw a bunch of solar panels onto the grass next to a runway. Airports have to carefully mitigate some really severe risks. First up, standard solar panels reflect light, which could cause temporary blindness or glare for a pilot coming in for a landing. So special anti-reflective coatings are absolutely mandatory. Second, roof-mounted solar panels emit electromagnetic waves that can disrupt sensitive communication and surveillance systems, meaning special shielding is required. And third, well, if an aircraft has a veer-off accident and skids off the runway, crashing into high-voltage solar arrays could spark a catastrophic fire and severely hinder rescue teams. So strict safety distances are absolutely vital here.
To handle those massive 3.75 megawatt charging spikes we talked about earlier, airports are going to have to balance fast-responding battery banks with long-term hydrogen storage tanks. Picture this. When the sun is shining, the airport will store all its excess solar power in giant stationary battery banks. These batteries can then discharge instantly to help the grid handle the massive power spike of a plane plugging in. Meanwhile, any leftover excess energy can also be used to generate hydrogen. This hydrogen can be stored long-term and dual-purposed, either fed back into the local grid during a cloudy week or pumped directly into a hydrogen-powered aircraft. It's like a giant, incredibly smart energy buffer. So what does this all mean? Well, hopefully this explainer changes your perspective a bit. The green transition in aviation is about so much more than just what goes up into the air. It requires a monumental reimagining of the Earth beneath it. Next time you're sitting at your gate, just look out the window. I really hope you'll ponder the massive hidden engine of infrastructure, the megawatt chargers, the crazy cooling systems, the hidden solar grids, and the cryogenic hydrogen tanks, working tirelessly below the wings to make sustainable flight a reality.
Thanks so much for joining me on this explainer, and keep learning.